study of kinematics. Kinematics is basically the study of motion, all right? So basically I'm going to tell you somehow, mathematically, one way or the other, something is happening, something is moving, and we're going to try to describe that motion in terms of position, acceleration, velocity, speed, these sorts of things. We'll start out in one dimension, all right? But then being discontent with one dimension, we'll move on to two, and then three. Sad things out there. Until the end of the course, and then I'll tell you about four dimensions a little bit. So, in one dimension, we don't really need vectors. One-dimensional motion, we're going to talk about direction in one dimension. It suffices just to use the sign of a number, right? So, a variable being positive might indicate it going to the right. A variable being negative would indicate its motion to the left. Or it could be that positive is up, negative is down. But all this, all these things I was telling you about vectors, well, those will come back, but we don't really need them so much today. So let's talk about motion in one dimension. The other thing I'm not talking about today is why there's motion. All right, so you know, my starting point will be, suppose the motion is going this way, right? We leave aside the question, why is the motion happening that way for a later time? Study of what causes motion, the relation of, the causation of motion by force is the study of dynamics. That comes later in this course, all right? So, okay, so motion in one dimension. What are the basic things we want to talk about? First of all, an event. What's an event? It's a time and a place. So, for example, if we're using x, perhaps x comma t. I guess I should say t comma x, I don't know, whatever. So that would be an event, right? So if you have two events, then you can do other things, right? Two events. Suppose I have, say, x1, t1, and x2, t2. Well, then all of a sudden you can do things like you can calculate the displacement between those two events, right? So displacement would be what? So the displacement from event 1 to event 2, I usually use the notation change in x upside down. Oh, it's the triangle's right side up. I don't know. Anyway, it's a triangle. So change in x, that's simply x2 minus x1. Right, the sign of the displacement is interesting, right? If x is the coordinate in the horizontal direction, if the displacement is positive, that means the motion is to the right. If the displacement is negative, the motion's to the left, right? I mean, correct. So there's displacement. What else can you talk about? Well, how about average velocity? Average velocity, another thing we can talk about. So average velocity, the average, will be the displacement delta x over the duration delta t. So the change in time divided into the change in position. This gives me average velocity. Okay, so explicitly, this is x2 minus x1 over t2 minus t1. Right. Now, of course, a lot of times, I mean, we use this all the time in our daily life, right? Like, you're thinking about traveling somewhere, you're saying, well, I'm going to travel 50 miles per hour, and how long is it going to take me to travel, 200 miles? So what do? 200 miles, say I got 50, I need four hours, right? So now, how does that work mathematically? Mathematically, we have, delta x equals to 200 miles. The average is 50 miles per hour. And so to figure out the time then, I could say, aha, well, delta t, let me see here, a little bit of algebra, right? The average is equal to delta x over delta t. So how do I find the time? Do algebra, right? Solve for delta t. Delta t is equal to delta x over v average. Okay, so for my silly example, that would be 200 miles divided by 50. And I'm going to get rid of miles per hour and trade it for something more useful, which is miles per hour, but I'm going to write it in a better way, right, as a fraction. So you can see how the units work out, right? So the miles cancel. 1 over hours gives me hours. 200 over 250 is just 4, right? So 4 hours, there you go. So this is average velocity. Now, the only way that that makes sense is if what? The velocity is constant, right? Or if you don't care about the details of speeding up and slowing down, right? This gives you a kind of gross idea of the motion. And there are interesting questions you can ask about average velocity. Here's one that the answer might not be entirely obvious, you know, just from this kind of reasoning. Hopefully it will work. Come on. Come on. I'm doing an experiment. I'm not wearing the mic today to see if it still picks up the voice well enough. That way, in the event one of you asks a question or has an interesting conversation, I'll hear it. So, see here. Also, the mic is scratchy and I don't know how to fix it. Okay, so here's a question. Suppose Superman. Oh. Really? What? That's. One of you work for IT. Someone here is sabotaging me. Here. All right. So suppose Superman is a little slow due to excessive cloudy weather. You know, shielding the warmth of our yellow sun. Right. So he's a little bit down, and he's only flying about 500 miles per hour. All right. And then there's 2 trains on a collision course. All right. And the trains have speeds of 80 and 50 miles per hour, and they begin 150 miles apart. So you get these 2 trains coming at each other in a collision course. There's evil robots keeping them from stopping. I don't know, you pick your favorite. I don't know. Yeah, it could be cats, right? Evil robot cats. Yes, very good, very good. Then the question is, how far does Superman travel as he flies back and forth between the trains, trying to stop them? I mean, he's, for some reason, just flying back and forth between the trains, trying to tell them to stop. I don't know why he's doing this. He's Superman. He doesn't need a reason to do things, right? I mean, just plot convenience, right? In this case, make my examples convenience. So suppose Superman's flying back and forth between these 2 trains, back and forth and back and forth and back and forth. How far does he travel before the trains collide? Or suppose he stops them just at the very last second. Typical cinematic fashion, right? Well, if you think about this, this is really a problem of average velocity, because he's Superman. It doesn't take any time for him to reverse direction, right? So Superman is always flying at 500 miles per hour. The whole process of this, right? So to figure out how far Superman travels, I just need to figure out how much time it takes for the trains to get together, right? And so that's what I do. I just calculate how much time it takes. Now, how would you calculate how much time it takes for the trains to get together?
Average similar speeds.
Yeah, you're like, so if one's going 80 miles per hour one way and the other one's going 50 miles the other way, effectively they're going 130 miles per hour towards each other, right? So if I have 150 miles, 150 miles is the delta x, the effective speed is 130 miles per hour. How do I figure out the time then?
150 miles divided by 130.
Yeah, 150 over 130. Miles cancel, we get hours, whatever that is, right? Then what's the delta x for Superman? it's 150 over 130 times 500 miles per hour, right? So there actually are kind of, I think this is a slightly interesting problem. Here's my solution. Now, I like what the gentleman in the audience said, use the effective velocity. Basically, you're using relative motion, which is a section we won't cover until later. That's true, that's a fast way to see it, but a different way to see it is just to write down the position as a function of time for one train, the position as a function of time for the other train, and look for where their position functions are equal. That's the point at which they intersect. So for those of you who didn't see the 130 miles per hour trick, this is a way we can do it. Right? There's a question?
If delta t is in hours, then would you have to divide 500 miles by delta t rather than multiply them? Or is it?
Wait, well, I mean.
Oh, okay, never mind. I see what you're saying.
Yeah, sorry. Okay, so this was in hours,
Yeah.
and then it's 500 miles over hours. So of course the hours cancel, leaving us miles, as we would like. So I took a slightly different approach here, which is just to say, well, the point where they come together is the point of intersection. So if I put train A at position 0 at time 0, this is its equation of motion, 80 miles per hour times t, right? If I put train B at 150 miles at time 0, then it's got a speed of 50, so minus 50 miles per hour. That's the equation of motion for train B. And then I equate those to find out that the time when those position functions are equal is, of course, 150 over 130. I mean, all roads lead back to that answer, but this is a slightly less sneaky way to do it. The sneaky way, which was suggested, is a good way, but here's another way. And then, of course, once I have the time, I multiply by Superman's speed, and there it is. Okay, so put this away. Now, when I talk about velocity in here, I do not mean average velocity. All right? Let it be understood. This is calculus-based physics. When we talk about velocity, when I talk about acceleration, whatever, I am talking about the instantaneous velocity or the instantaneous acceleration by default. So how do we define those? So we have to calculate v of t is equal to the limit as delta t goes to 0, right, of x of t plus delta t minus x of t divided by delta t. Or if you like, I could say it's the limit as delta t goes to 0 of delta x over delta t, right? The limit of the average velocity as the duration shrinks to 0. This is instantaneous velocity, which again is velocity. All right, so yeah.
Is that t plus changing t on top?
Yeah. I mean, you could do minus, it wouldn't change anything mathematically. I mean, for what it's worth, you could look at this limit in terms of like the symmetric difference. You could do this if it floats your boat. Same thing. Different looking limit calculates the same quantity. This is a double-sided limit, so I mean delta t is going to 0 from the left and the right. We learned in calculus this is the what? This is the derivative. Right. This is dx dt. So dx dt, there you go. This is the instantaneous velocity of time t. For a given position function, obviously, right? Now, how do we define acceleration? How is acceleration defined? We use a, it's equal to dv dt. I could tell you in terms of a limiting process, but let me get to the point. Pragmatically speaking, what is the derivative? It's the rate of change, right? This gives us the instantaneous rate of change of the velocity with respect to time. This is called acceleration. All right? So, get this calculus out of our system. We can talk about the position, the velocity, and the acceleration all at once, right? So one discussion you might have is the meaning of, say, velocity time graphs, right? You guys have looked at velocity time graphs before? Maybe, maybe not. So let's see, suppose we graph velocity in the vertical direction and we graph time this way. Right? And then, okay, so suppose the velocity of a function, velocity looks like, I don't know, how about this? So here you go, here's v. We can talk about the significance of a couple different things with respect to that curve, right? So let's pick at two things. First of all, suppose I pick this time, say t1, right? Time t1, and I look at the tangent line for this graph, right? What's the slope of this tangent line? The acceleration at time what? At t1, right? Now this velocity graph is an example of a non-constant acceleration, right? The acceleration is changing. You go to different points on this graph, the velocity function has different slopes, right? So this would be a non-constant acceleration. How do I see something about position from this graph? How would I get, or displacement perhaps is better to talk about. How about displacement? Say the displacement from, say, time 0 to time 1. What would that mean?
The integral from 0 to time 1 of the velocity.
So I heard the integral from 0 to time 1 of the velocity of t dt. That would give me the displacement, the delta x. I agree. Now, let me show you why. It's the net change theorem from calculus, right? So this is equal to the integral from 0 to t1 of dx dt, right? That was the definition of velocity, dx dt. And what is that? Well, what's the antiderivative of dx dt? What function can you differentiate to get dx dt? Well, yeah, x. So FTC part 2, this is x of t1 minus x of 0, right? Which is exactly what I wanted, right? That's the displacement from time 0 to time 1. So, in terms of the graph that I have right there, what's it look like? Did I hear it's going to be awesome? Okay, I'll take it. Maybe a slight misuse of the word, but it's this right here, this area. That area on the graph corresponds to the displacement of the motion considered, from time 0 to time 1. So, of course, as another remark, if we want x of t, and we know x of 0, say, is equal to x of naught, then the following is a nice formula to know. X of t is equal to x of naught plus the integral from 0 to time, let's say, t, of, well, v of u du. I mean, I can't use t there because t is the meaning of time. It's already used up. I could use some other variable of integration to be correct, but there you go. I mean, that's, you can get the position as a function of time from integrating the velocity, right? How would I get the velocity from the acceleration? Pretty much the same way, right? So since A is equal to d dt, if we know that v of time 0 is v sub naught, like that's some given constant, then v of t you can also derive is v naught plus the integral from 0 to t of a of u du. Now, some people don't like to use u here. They want something that makes you think about time. So one thing I could do would be to put like a, some people use t-bar, other people use like a tau, because it kind of looks like time, but it's not. The point is that if this is the time over here, I can't use the same symbol. It's already used up. Time has a fixed mean there. Okay, math. Okay, let me try to get some more calculus out of my system here. The other interesting question that kind of tests your understanding of the relation between velocity, acceleration, and position from the perspective of calculus 1 is the relation just graphically between the velocity, the time, and the position graphs. So sometimes it's fun to try to draw all three on one given graph. Like one thing I could have done here is I could try to go. Let me start with, well, I'll attempt to recreate my velocity graph there. So this is the velocity. What would the position look like? I'll draw the position in green. So first of all, you could be like, well, I don't know, right? For example, I tell you, my brother's driving here in a car going 100 miles per hour. Where is he? Is this a reasonable question? No. That speed is reasonable for my brother, but I didn't tell you where he is, right? So you don't know if he's over at Walmart or if he's in Kansas. I mean, whatever. You need an initial position, right? So let's take the ambiguity out of this and say that the initial position is at the origin, just for graphical purposes. Then what does the position function qualitatively look like past this point? Well, the velocity is a parabola. Yeah, maybe. The velocity is positive, right? So the position function's increasing. Definitely the position function's increasing. And it's increasing at a faster and faster rate. So, yeah, maybe something concave. Maybe roughly speaking, that could be x. How about acceleration? What's acceleration look like? I'll make that one purple. Oh, maybe blue. Acceleration is the change in the velocity, right? So what's happening to the velocity? Is it going fast? Is it going faster? Well, I guess you guys are right. The velocity is, looks like that the velocity is about leveled off right here, right?
About 0.
So, yeah, let me just make it blatantly so. Okay. So there's some kind of horizontal tangent in the velocity up to the limits of my artistry. And so that makes the acceleration be 0, wherever the velocity is stopping increasing and starting decreasing, or vice versa. That's a place where velocity has to be, the acceleration must be 0. So, all right, so acceleration 0 there, and it looks like it's negative over here. Oops, maybe not that extreme, but whatever. And positive. Here, just to make it interesting, maybe this happens. So then, that would put a 0 back in the velocity. Okay, I'm sure I've assigned you at least one of these problems. It's always a nice test question. Here's 3 graphs. Identify one is the position, one is the velocity, one is the acceleration, right? There's no calculation, it just depends on your understanding of the graphical relation in these time, velocity, acceleration, position. Okay, now, so there's one very important example that we spend a lot of our time on, which is the case of constant acceleration. So what does it mean to have constant acceleration? Is it like constant with respect to politics in America? I mean, Doesn't matter if the Republicans or the Democrats are in power, anyway, this acceleration is the same. I mean, constant with respect to what? Time, yes. Time. So what that means then is that dA dt is equal to 0. That mathematically is what it means for something to be a constant, right? Its derivative is set equal to 0. So if that's the case, what does that tell you about the velocity? Right, so that means that,
The velocity is constant.
let's see, so dv dt
It's not the rate of change.
is equal to a, right? Oh, I'm sorry. What does this mean, though? Let me just say that this means that a is equal to a naught, and this is some fixed constant, right? So I just slap a little sub naught on it to make you think about it being a number as opposed to being the variable representative of the change in velocity. So let me just put a little naught. Emphasize it's constant. So, okay, so here's what we do. Multiply both sides by dt. dv is equal to a sub naught times dt. So I'm doing what's called separation of variables. And, okay, then I integrate both sides. And so, let's see here. So I will integrate, and to be fair, I have to integrate over matching bounds. All right, so like v should be integrated, say, from v naught to vf. The initial velocity to the final velocity. All right, so to be fair, I have to integrate the other side with respect to the matching bounds for time. So say from time naught to time final time, pf. So what's the integral of dv? V, right? So this gives me vf minus v naught, right? And on the other side, I have a sub naught times tf minus t naught, right? So there we go. Here's a formula for you. Vf is equal to v naught plus a sub naught times tf minus t naught. That's the relation between final velocity, initial velocity, and acceleration in the case that the acceleration is constant. Now, a lot of times, we like to talk about time t, and we like to set the initial time to be 0. Right? So if we set the initial time to be 0, and then what's this look like? A lot of times we'll use this formula. T naught is equal to 0. And the final time is just equal to t, then we might write the v is just equal to v naught plus a sub naught times t, right? So this more highfalutin formula just looks like that with those special choices. All right. What else might you like to know? Maybe position as a function of time? How will we get that? I guess I already told you over here, I kind of ruined the story now. But the thing is now we can actually do the integral because the velocity it's not some wacky arbitrary function of time, it's the line. Right? It's v naught plus at essentially. Okay, so let's see here. So let's see, suppose the velocity at time 0 is equal to v naught, and the position at time 0 is equal to x naught. These are given constants that describe the motion, okay? And also, I'm assuming that a is equal to a sub naught. We know a constant. So let's find x of t. All right, so we already have worked out that v of t is equal to what? V of t is equal to V sub naught. Plus a sub naught times t. I'm basing the motion at time 0, just to be specific. This is equal to what? This is equal to dx dt, right? Tell you what, I'm going to separate and integrate again, just because you guys are less used to that, and it's good to see. So, let's see here. So multiply both sides by dt, right? And I'm gonna put the dx over here. So I've got dx is equal to v naught plus a sub naught times t, all times dt. So that's called separating variables. I want to know what x is, right? So I integrate both sides to figure that out. Again, to be fair, I need to integrate over bounds on both sides which are matching. So if I integrate the left side here, say from x naught to x, and I mean, I guess to be fairly pedantic about it, say x of time t, then I should integrate from time 0 to time t over here. Oh, see, now I feel guilty. I have used t in a wrong way. How can I fix it? I won't actually take off points in here if you do this, but in a calculus class I might. So like, yeah, I need to, I mean, this t here is different than that one. This is the fixed time we're trying to understand the position for. This is the time which is appearing in the integration. I mean, this is the dummy variable integration. So I don't know, just slap a tilde on it or something, then nobody can complain. All right, so anyway, silly comments aside, this is x of t minus x of naught is equal to integrating v naught gives me v naught t, and then plus 1/2 a naught t squared. And there you go, one more step, and then I have our handy dandy formula which we like to use. X of t is equal to x naught plus v naught t plus 1/2 a naught t squared. And that is the position in terms of the initial position and initial velocity in time in the constant acceleration case. You need to not only understand how to derive this formula, you need to understand how to use it, and you need to understand how not to use it. So how do you not use it? When do you not use the constant acceleration formulas?
When the acceleration is not constant.
When the acceleration is not constant. I have you all on record as saying that. Not you? Okay, then I can't mock you when you do it. But the rest of you, haha! For shame when you put the non-constant acceleration, we put the constant acceleration formulas into the non-constant case. Oh my goodness, the things I've seen, the atrocities. Poor math. What did math ever do to you guys? Horrible things. Okay, well this is great and all, but there are other formulas that we would like to know about. Let me derive them for you. I have oodles and oodles of examples to show you, don't worry. But we should get the math out of the way. In the constant acceleration case, it's convenient also to relate the position to the acceleration directly. So here, there's a really sneaky trick that I'm very fond of, and here's how it goes. So A is equal to dv dt, right? But if you just tilt your head and squint, you can see that what you really got there is dv, well, what is this? Well, I mean, that's really just the same as, I mean, I could write dx dt times dv dx, right? I mean, I'm just dividing and multiplying by dx. Surely that's allowed. For the more mathematically inclined, this is the chain rule. Assuming that the position is completely parametrized by the time, this would stop being true in higher dimensions or places where there's more than one coordinate. True, you know. And so what is this? This is d dv dx. I love the way that sounds. d dv dx. See, because that's velocity. Now I can separate variables, and I got myself a v dv is equal to a dx. keeping with the theme today, we have to integrate both sides over bounds which are matching. That, by the way, is just u substitution. Just u substitution, something more than that. But, so here I should integrate, say, from v naught to vf. And on the other side, I should integrate over the matching bounds for x naught to xf, the final x and the initial x. What's the integral of v dv? 1/2 v squared, very good. So on the left-hand side, we've got 1/2 vf squared minus 1/2 v naught squared, right? On the other side, we've got what? A times xf minus x naught, right? And then I'll solve this in the, maybe just solve for vf squared, make it all nice and pretty.
So wait, is this A the same as the A naught that has been used in the previous?
Oh, yeah, I'm sorry. Let me add some knots. Knot. 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 All right. That's good. I didn't want this to be all for naught. So, vf squared equals v naught squared plus 2a sub naught xf minus x naught. And there you go. This is an awesome formula. I call this the timeless equation. See why? You could say, what's the physical significance of this equation? That would be a good question to ask. This is conservation of energy. But that's a kind of mysterious comment for now. All right, so let me get out the old projector here. If I can't find us some good examples to point at. So these formulas you want to understand backwards and forwards and upside down. I mean, this is the lion's share of test one. It's more or less based on your ability to analyze vectors and also these guys. All kinds of fun questions we can look at. Let me find a sufficiently fun one to start with. Here's one. And this is the Postit Notes, so if you mostly just want to follow logic. If you can't write this all down, it's not a big deal. These are posted on the website. Yeah.
Would you be against if for the second formula it was x of t equals x of o plus b of t plus 1/2 at squared? Would you be horribly offended if trying to think of how to phrase this. If we change it to delta x equals b of t plus 1/2 squared?
No, that's also true.
Okay.
That's just another way of writing the same thing. Basically, the gentleman is asking, can you take the x naught to the other side in the position formula for a constant acceleration case? And like, yeah, you can also write delta x is equal to v naught t plus 1/2 at squared. Same animal. Yes, sir.
Should we know how to derive these equations for
Yes.
the test?
Yes. Sir. One of my great joys as an undergraduate, I started working for this thing called the Physics and Math Tutorial Center at NC State back in the day. I made good money tutoring people when I wasn't playing Doom with my friends there. We had IMAX, it was awesome. But people would always ask me, inevitably ask me, they'd be like, could you help me with this web assigned problem? Which basically means, could you do your homework? Could you do my homework for me? And I always made them pay a tax. And the tax I made them pay was that I would derive these formulas for them. So I've derived the constant acceleration formulas literally hundreds of times, just as a sort of a, well, I'd like to do it, I don't know, it's kind of a psychological problem I have, but that's the funny thing about mathematicians, I was like, we're really only happy if we have problems. It's the life we live. I don't know if I'm a mathematician, by the way, but anyway, suppose a car has brakes. That's good. And thus apply apply a constant deceleration of -2 meters per second squared. All right. If the car has an initial speed of 20 meters per second, then what's its stopping distance? Okay, so this is made to order for the timeless equation. I don't care about the time, right? I know the initial speed. I know the acceleration. So there you go. The final, and it stopped means what? Zero velocity, right? So I can say 0 squared is equal to v naught squared plus 2a delta x. And there you go. I get 20. So again, the v naught is 20, and the acceleration was -2. These minuses cancel, give you a plus 100 meters. Pretty typical example. Now, I added a little bit to that question. I said, how fast? How much time did it actually take for that to happen? Now there I would have to go back and use the VF equals, this equation, VF equals V naught plus AT, right? Well, the time is going to be the final velocity minus the initial velocity divided by A, right? I know the final velocity is 0. I know the initial velocity was given, 20 meters per second, right? And the acceleration is -2, so there you go. 10 seconds. I could have done this before I did that, right? These are interdependent. Let's see here. In the same example, what was the average velocity of the car as it was braking? So the average velocity would be the position, which we figured out, the braking distance, 100 meters, the time, 10 seconds, divide those two, that gives you the average velocity during the braking, 10 meters per second. I probably should have a minus on that. Being careless about the sign here. Well, yeah. That's a plus if the other one's a plus. I'm sticking to my guns. All right, so 10 meters per second is the average velocity.
I think mathematically it should still be a positive 10, shouldn't it?
Well, it kind of did.
Because it's still moving.
Yeah, you're right. No, yeah. Gentleman's right. I shouldn't debate. Signs are fine. Now, graphically, it's interesting to look at what just happened in terms of velocity time graph. If you constant acceleration, then the velocity graph is just a line, right? Because it has constant slope. The slope of the velocity time graph is the acceleration. So constant acceleration means constant slope for the velocity graph. Now, here's what's going on. This is the initial, the initial velocity. Well, let's see, where am I? X2, what am I looking at here? X2. I'm deriving something more general down here, but the slope is wrong. This does not help us. This does not help. This is not part of that example, is it? Why?
It's the other way around.
What's the acceleration is what? It's negative in the examples we were just talking about, so I'm going to have a really hard time interpreting the last couple of examples in view of this graph. This graph is just a more general comment. The comment of this graph, and listen to this, is that the average velocity is the average velocity. Excuse me, the average velocity is the average of the velocity. There's two different ways you can think about average velocity. You could say change in distance divided by change in time, right? That's your high school average velocity. Or you can talk about the average of the velocity, as you talk about in calculus, which is what? It's the area under the velocity graph divided by the length of the independent variable, which in this case is t2 minus t1, the duration, the change in time. And this calculation here, actually, I'm just deriving basically that for the constant acceleration case, actually, I just take and work it out, do math. I actually get 1/2 of the initial velocity plus the final velocity. I mean, it's also the average of the velocities in this case. You see what I'm saying? If you take the initial velocity plus the final velocity, divide by 2, you get the average velocity. There are actually 3 different ideas we could use here. This is, what was this called when you take 2 numbers together and you divide by the total? You have to n numbers. Yeah, but there's a word for it. The mean, right? Yeah. there are problems that you have to solve using this. Those are useful problems, but they exist. They do exist. All right, so conceptual checkpoint. X denotes position, the velocity, A denotes acceleration, which again is the change in velocity position. Velocity is change in position. There's a picture here I wanted to show you. This is a quintessential confusion is if the position is 0, the velocity must be 0. If the position is 0, I can't say anything about the velocity. I don't know what the velocity is. I could be speeding up, I could be slowing down, I don't know. Likewise, if the velocity is 0, I can't say anything about the acceleration right off. Velocity 0, I could have negative acceleration, I could have positive acceleration. I don't know which way the thing is going. Like, think about a car at a stoplight, right? Before it's speeding up, its velocity is 0, its position could be 0, its acceleration could be 0, right? The moment you hit the gas, your acceleration is positive, but the velocity is still 0. Right, at the initial start, right? I mean, if you start thinking about this, there's no direct link between one and the other. Well, that's too much to say, but here's a picture. Oh, there's a guide to the calculus to get from, position to velocity, differentiate. I don't know what, somehow my D got chopped off right there. I don't know what's going on there, that's weird. It's supposed to be a DDT right here, right? It's weird. I don't know, how'd that happen? Okay, probably a cat. All right. Oh, check it out. What's this? So, well, I think here I suppose I have, what's J? Oh, here I've assumed that I don't have a constant acceleration, but I have a constant jerk. You know what the jerk is?
It's the same thing except.
I was looking for a specific student, but he's not here. You know who you are. It's the third derivative. So the derivative of the acceleration with respect to time is the jerk. If you've ever been on a train and like you've gone from like a flat section of the track to a curved section, you ever notice that there's this I don't know, that's it. You're experiencing non-zero jerk right there. So a change in acceleration is a jerk. It kind of what it sounds like. It's a jerky motion when it's non-zero. Finally, the picture I want to show you guys. So this has some different cases, right? So if you're thinking about a ball dropping, what? Oh man! I could blame cats, but we know it's just me. So, can you tell me what direction this arrow should be going if the ball is dropping?
You could say you dropped the ball and it's probably.
So, but my point to you is whether the ball is dropping or decelerating upward or being thrown upward. Either case, gravity does this. Oops. Right? So, gravity is very boring. Like, no matter how many times you drop a marker, there's no time it does this, right? Like it always wants to do. I mean, unless it's an episode of Fringe, right? There's this awesome episode of Fringe where gravity goes backwards, people start like flying off into the sky. Kind of disturbing, right? Imagine like careful when you go outside. Don't forget to put on your shoes. Otherwise you'll fly into the sun. We live a very easygoing life. We just walk outside without even thinking about it. So anyway, and then a car speeding up, you have velocity and acceleration in the same direction. But when the car is braking, the velocity is positive, yet the acceleration is negative. So what I'm trying to tell you is the signs, the plus or minus of acceleration, position, velocity, they're, we will always ask you these multiple choice questions that try to tempt you to suppose when one's 0, the other one's 0, or when one's positive, the other one must be positive. But in fact, the choices are many, and you have to think about it. Okay. So, oh, and that's all I have for today.
Why does President Lincoln have a baseball?
That's not President Lincoln, that's Mr. Top Hat. Would that be clear? That's Mr. Top Hat.